Good day, class. In this video, I will teach you the step-by-step coding of the simulator of the Cartesian Manipulator. Okay, so I already created a script named Cartesian underscore sim. Okay, so first, let's just create a display title named Cartesian Manipulator. Okay, then at the section of link lengths, so we have uh, 4 link lengths, so A1 to A4. So let's name them. Okay, I forgot. So let's have independent variables of A sub 1, the link lengths, A sub 2, A sub 3, and A sub 4. Okay, so keep reminded that the link lengths are constants, but because we don't still have a value for the link lengths, so let's make them individual variables. Okay, in this link length part, so we will give them values. Okay, so let's try first the values 3, 8 to is equals to 3. So let's assume that Peter Corke units of length is meters. Okay, A4 is equals to 3. Okay, then down here at the dx parameters section, okay, we have here a rule on how to arrange the parameters of our dx parametric table. Okay, so we have here the at this arrangement, the theta, the d, the r, the alpha, and the offset. So we don't have offset as a parameter in our discussion of parametric table, but this parameter is useful in coding the simulator here in MATLAB online. Okay, so the offset uh, will be used to construct the prismatic joint of our mechanical manipulator. Okay, so because this is Cartesian manipulator, we will use the offset. Okay, so there are rules in using the in coding. Okay, in coding the parametric table. Okay, so these rules are some of the rules. I just summarize some of it. Okay, if we are coding the prismatic joint, okay, theta will be equals to theta, d is equals to 0, offset is equals to 1, and after offset, put the value of d. Then if revolute joint, theta is equals to 0, offset is equals to 0. After offset, put the value of theta. Okay. So to elaborate these rules, okay, I will show you the function and the syntax of the code of our simulator. Okay, so first let's have the h01 variable. Okay, h01 variable, so it's equals to link. So this is our function, link, close open parenthesis, and inside it is a square parenthesis. Then we will put a semicolon at the end so that it will not reflect at our command window. It's fine if you want it to be reflected at our command window, but for the purpose of showing the important details in our command window, I will use the semicolon. Okay. So inside this link, okay, this link function, the syntax says here is this. So first is the theta, then the d, then the r, then alpha, then offset. Okay. So what we will put here will be based on our parametric table. Okay. So our theta is 0 based on our parametric table, based on the first, okay, based on the first row of our parametric table. So this is 0. Then next is D. Okay. So we should put here A sub 1, but based on what is the rule, if prismatic joint, D is equals to 0. So we will also put here 0. Then next is R. R in our parametric table is 0. Alpha is 270 degrees. Okay, so to put 270 degrees in MATLAB, we will convert it into radian in terms of pi. Okay, so 270 degrees in radian in terms of pi is 3 times pi over 2. Okay, then after alpha is the offset. Based on the rule here, if we are coding prismatic joint, offset is equals to 1. Okay, offset is equals to 1. Then after offset, we will put the value of d. Okay, so d is equals to a sub 1. So let's put here a sub 1. Okay, so this is the first link. Okay, from frame 0 to frame 1, or H01, homogeneous transformation matrix of frame 1 relative to frame 0. Then after that, okay, H01, again, the H01 variable. Then we will use the function .qLimit, okay, or .qlim, then equals to square parenthesis, then semicolon, okay, semicolon outside. Okay, inside the square parenthesis, we will put 0 and 0. Okay, so what this function do is it creates a limit. Okay, it creates a limit for our prismatic joint. Okay, so our prismatic joint has a limit. Okay, has a limit length. Okay, it has a limit length. The limit length also can be described using the joint variable d. Okay, can be used to describe by joint variable d. Okay, so what we will put in this inside this square parenthesis, okay, are the limits of our joint variable. Okay, are the limits of our joint variable. So it's 0 and 0 because our first link is a stand. The first link is a stand, so it doesn't move. Okay, it doesn't translate. Okay, so it's only described by the link length A1. Okay, so it is 0 and 0. Next, for H12, H1 underscore 2 is equals to, again, link. So open parenthesis, then inside is square parenthesis, then semicolon. Okay, our theta is 270 degrees. So it is 3 times pi divided by 2. Okay, next. 3 times pi. Oh, sorry. The next one is D. So D is equals to 0 because this is prismatic joint. Next is R. Our R is 0. So we are at the second row. Okay. We are at the second row. Next is, so 3 times pi over 2. dr alpha is 270 degrees. So 3 times pi divided by 2. Then comma. Then next is alpha. So this is prismatic joint. Alpha is equals to 1. Then after offset, okay, after offset, put the value of D. Okay, the value of D is A sub 2. Okay, we will not add D sub 1. We will not add D sub 1 because we will use D sub 1 at our limit. Okay, so enter. So H12 is equals to Q, H12 dot Q limit is equals to square parenthesis, semicolon. Okay. So here, we can say that our limit is from 0 to D sub 1. Okay? From 0 to D sub 1. Okay? This is where we will put the joint variable D. Okay? So, D sub 1 has no value yet. So, we will put a value for D sub 1. Our D sub 1 will be the limit of our prismatic joint. Okay? From 0 to whatever D sub 1 is. Okay? So, if we want to put some value for D sub 1, we will add D sub 1 at our sims. Okay? Then, under A sub 4, we will add D sub 1. Let's say it is equals to 5. Okay, it is equals to 5. So, it means our translation is limited from 0 to 5 meters. Okay. So next is H23. H2 underscore 3 is equals to link again. Close open parenthesis. Then square parenthesis. Semicolon. Okay. So theta is 90 degrees. So theta 90 degrees in radian in terms of pi is pi over 2. Okay. Next is D. Okay, D. So this is still a prismatic joint. So this will be 0. Next is R. Okay, so our R is 0 at the third row. Then our alpha is 270 degrees. So 3 times pi divided by 2. Okay. So the next one is after alpha is the offset. So our offset is equals to 1. And then our D is A sub 3. Okay. Then enter. H2 underscore 3 dot Q LM is equals to square parenthesis, semicolon. So our limit is from 0 to D sub 2. So we will also add D sub 2 in our sims. Then we will put some value for D sub 2. So let's say it's also 5. Okay. or 2. Okay, 2. Yes, or do you want make it, let's make it also, no, 5 or 3. Okay, let's just make them all 3. Okay, let's make them 2. Okay, 2. Okay, that's fine. Next, for H34, our last row in our DH parametric table. So H3 underscore 4 is equals to link, close open parenthesis, square parenthesis, semicolon. So our theta is 0. Our D will be 0 because this is prismatic. Our R is 0 and our alpha is 0. Our offset is 1. Our D is A4. Okay. Then for our limit, so H3 underscore 4 dot Q LIM is equals to square parenthesis 0 to D3. Okay. So let's add D3 in our seams. Then D3 for our link lengths. So D3 will be 2. So let's put another section for joint variables. Joint variables. Okay. So these are our links from the base up to the end effector. Next, we will compile the links using another function called serial link. So we will make a variable named cart for Cartesian, then it is equals to the function serial link, close open parenthesis, then square parenthesis. Inside the square parenthesis, we will put the variables h0, 1, h1, 2, then h2, 3, then h3, 4. Okay. Then outside the square parenthesis, comma, we will name our mechanical manipulator. To write a name for our mechanical manipulator, we will first write the command name. Then after that, the string cart as the name of our mechanical manipulator. So this is the string. Okay, this cart is the string. The name is the command. Okay, they are both inside a quotation mark, a single quotation mark. Okay, in Python, only the strings are inside the quotation mark, but here in MATLAB, there are commands that are inside the quotation marks. Okay, so let us not put some semicolon there. We want to see what will be the output of this function serial link. Then we want to plot our code. If I say plot, it means we will simulate the code. Okay, so there will be a plot of this code where we will see the simulation. Okay, so plot, then close open parenthesis, then square parenthesis. Inside the square parenthesis is 0, 0, 0, 0. Okay. What does 0, 0, 0 means? Okay. So 0, 0, 0 0, 0, 0, 0 means 0, 0 means that our mechanical manipulator is at the value of 0. Okay? All the joint variables value will start at 0. Okay? This is also called the origin position. Okay? In industry, it is called origin position. So it means all the joint variables have the value of 0. So let's put that in here. So plot, okay, sorry, percent plot at origin position. So origin position means all joint variables are equals to 0. Then comma, let's put the command workspace. The command workspace, okay, is used to have a workspace, a Cartesian coordinate system workspace, where our mechanical manipulator will be constructed. Okay? So, the workspace have the coordinates of our Cartesian coordinate system. So, again, square parenthesis, then inside of that square parenthesis is the size of your Cartesian coordinate system. So let's say the size of your x-axis is -10. Okay, so let's make this larger. -10 and +10. So this is the x-axis. Okay, next the y-axis. Let's say also it is -10 and 10. Then the z-axis is from -10 to 10. Okay. So, this is our code for plotting our mechanical manipulator or simulating our mechanical manipulator. So, notice if there are red colored signs at the side of your program of your script. So if there is a red colored sign, it means there is an error. So this is are all orange and gray. So they are, our code is fine. Okay, so let's run this. Let's press F5. Okay, so what will happen is it should have a figure 1. Okay, then inside the figure 1 is the plotted Cartesian manipulator. Okay, so this is the Cartesian manipulator at the origin position where all joint variable is 0. Then at our command window, we have here the DH parametric table. Okay. Brought to you by Peter Corke. Okay, Engineer Peter Corke or Dr. Peter Corke. Okay. So in Peter Corke's parametric table, okay, the theta is 0. Okay. This is 270 degrees, then 90 degrees, then also 0. D is equals to, okay, so the D is the main joint variable because these are all prismatic joints, so it's not the same with our D. Okay, it's the same with the offset. Okay, the D will be the same with the offset, not with the joint variable D. Okay, next is the alpha. So this is alpha, all are 270 degrees. A means R. Okay, in Peter Corke's robotics toolbox, A means R. So they are all 0. Okay, so this is what this DH parametric table means. So based from what we did, the configuration is P, 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 prismatic, 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 or just only 3 P, three-piece, prismatic, prismatic, prismatic. Okay. So let's go back to our program. Okay. So this is the plot of our Cartesian manipulator. So if you want to maximize this figure, let's go here, click maximize, click this, then click maximize. Okay, so it's still small. You may zoom it using this tools. Okay, you may save it. You may I think this is change brush, just to brush, but I don't use it. This is the rotation. So if you want to look at it, okay, at different orientation, use the rotation. So this is the pan. Okay, this is the pan. So it's not functioning. Okay, this is pan. Just to move the mechanical manipulator. This is the zoom in, this is the zoom out, and this is home. If you click the home, it will just restore the view. Okay. So this plot, in this plot, we cannot change the value of the joint variable here. So let's close this. To change the joint variable in our plot, we will use the function cart.teach. Okay, cart is our Cartesian variable and that teach is our command. Okay, what will happen here? So let's a minute. Okay, let's CLC everything. Okay, what will happen here if I run this, a simulator will come up. Okay, so in our figure 1, we already have the simulator. Okay, so this is the teach simulator. Okay, teach. So I have already discussed this in our classroom, in our class. What does teach means? Okay. So this simulator is a teaching simulator. It teaches the values of the joint variables. Okay. So again, this is the DH parametric table brought to you by Robotics Toolbox by Peter Corke. So let's maximize this and see our final product. Okay. So it can be prettier. Okay. But first, let's try to navigate our slide switches. So our Q1, okay class, because this mechanical manipulator has a stand, the stand doesn't translate. We have here Q1 for the stand, but as you can see, if we slide the slide switch, it doesn't change anything in our mechanical manipulator, even though we put something here. Let's try to put something. Okay, it doesn't change anything. It's just an error. Okay. Okay. Oh, it changes the length, but don't mess with this because this is just a stand. Okay. So let's bring this back to 0. Okay, this is just a stand, so don't mess with the stand. Okay, for our first joint variable, which is D1, it was named Q2. Okay, if we change, if you change the value, it changes, it translates. Okay, the joint 1 translates. Sorry, that joint 2 translates because the joint 1 or the link 1 is a stand. If we slide the third slide switch, so it will the joint 3 will translate. Then if it's the fourth slide switch, the fourth joint will translate. Okay, so let's make this much better. Okay, you can make this much better. Okay, we have here an error because I put something inside here. Okay, I put something inside uh the s- the slide switch of the stand, so I should not put something here. Okay, so what I will do is just change the workspace to make this much prettier. Okay, so our mechanical manipulator is located at the surface, so I will just make the z-axis size from 0 to 10. Then the x-axis, I will just make x-axis, I think, negative 5 to 10, while the y-axis, I think, mm, because our Cartesian manipulator is just moving at the back side. Okay, at the at the backward side, or at the backward. So I will just make this negative 5. Okay, I will just make this negative 5. So our size now is negative 5, 10 at x-axis, negative 5, 10 at y-axis, and 0, 10 at z-axis. Okay, so let's uh, close this, then CLC at the command window. Okay, then okay, run again F5. Okay, so this is now our mechanical manipulator. So it became smaller. It became smaller. D3 is equals to 2. Okay, let's see. Maximize. Okay. Oh, I see, because it has the same size. Okay. Let's close this again. Let's change the value of A4. Let's make it okay. Oh, let's make A4. Let's see. Let's make A4 2. So 2. Then let's make D3 1. Okay. Or let's make oh, it's fine. Okay. Let's see what will be what will okay. Wait a minute. Let's subtract 3 at the x-axis. Let's make it 7. Okay, negative 5, 7, negative 5, 10, 0, 10. Let's see what it will look like. Okay, still small. Let's make the z-axis 7. Okay, this y-axis is also 7. Okay, let's see if it's still small. Oh, it's much bigger. Okay, so this is our Cartesian manipulator. Okay, so let's have a look at the end effector frame. Okay, we must check if the end effector frame is the same with our oh, it's still small. Okay, I will increase the length of a sub 1. Let's say 5. Okay. F5. Okay, it's much longer now. Okay, class. So let's look at the end effector frame. If it's the same with our uh, kinematic diagram. Okay, so x-axis should be pointing at the front. So this is front. Y-axis should pointing at the left side, while the z-axis should point downward. Okay, so this is right. The base, okay, at the right side is positive, at the left side is negative. The y, so positive side at backward, negative side front. Then for z, so this is upward is positive, so this is right. Our simulator is correct. Okay, so let's look at it at this orientation. Okay, let's orient more. Okay, this is fine. So let's slide the first slide switch. Okay. Okay. Then oh, this is 0. Why this is 0? Oh, this is just 1. Okay, this is the last slide switch is just 1. Okay. So small movement only. Okay. We may change it back here at our code. Okay. If you want to change something at your simulator, go back to your code. So let's make this D3. Let's make this 2. Okay. So again, so I forgot to CLC everything. Okay. So F5. Maximize. Okay, so this is our mechanical manipulator. If we slide, okay. Second joint, third joint, and fourth joint. Our first joint is a stand only. Okay. Or our first link is a stand. Our second link has a prismatic joint. The third link is a second prismatic joint, and the final link is a prismatic joint. Okay, so this is the coding of Cartesian Manipulator Simulator in Robotics Toolbox by Peter Corke.